Good morning. Thanks very much for joining this session of Google I/O. My name is Brad Chen, and I'm the engineering manager of the Native Client project. And I'm really looking forward to telling you about that, a little bit about that today. I also wanted to mention right away that we have other events planned for you today. There's a fireside chat at 1 o'clock and office hours for the Native Client project at 3 o'clock. And a bunch of the team members are here today. Can you guys say hello? We're looking forward to answering any questions you have about how to use Native Client, how to get comfortable with the system, that sort of thing. So let's get on with it then. Let's talk a little bit about Native Client and native code. Now, why would anybody want native code in a web browser anyways? I mean, it's been such a big source of problems in the past. Well, there's a number of really basic things that are motivating us. Firstly, performance. The JavaScript implementations that are available in browsers like Chrome nowadays are really quite incredibly good. But in spite of that, there's still about 2 orders of magnitude difference between what you can do with JavaScript and what you can do with native code. And the hardware architecture trends actually suggest that that gap is going to continue to broaden. Things like vector instructions and threading are just not useful features in today's browser for JavaScript-based systems. And so that performance, approximately 2 orders of magnitude, just isn't available. So performance is really the main thing driving us, and you'll see some other evidence of that as I tell you more about the system. Apart from performance, I kind of think that people should be able to use any programming language they want. They shouldn't be obliged to only use one particular language. And so native code and native compilation makes a lot of additional languages available. And not only are the languages available that you like them, but also all the legacy code that exists in those languages. And we're doing a lot to try and make it easy to import and use legacy code. So with these benefits, you might wonder, well, gee whiz, ActiveX and NPAPI, Netscape and Microsoft introduced those 10 years ago, so what's the big deal? Well, a couple of things you never got with these previous systems are portability and safety, right? An ActiveX plugin only runs on Windows, and NPAPI plugins typically do use the native OS interfaces, and so you can't move them from operating system to operating system. Moreover, because they have access to those native operating system interfaces, they have full access to the file system and full access to the network. They can do anything you want, which is, great on the one hand, unless you happen to be the recipient of such a module that wants to send junk mail or infect your computer with viruses. And so these are things that we've made very specific design decisions and done a lot of work to try and make much more difficult. Our goal in terms of portability and safety is to deliver a system that gives about the same level of portability and safety as JavaScript. And eventually, we'd like to even do better than JavaScript. So that's sort of the background on why native code. Now, what do we mean by performance? Because, you can write pretty fast JavaScript nowadays. Well, what we mean is literally we want to be within single-digit percentages of the best you can do with desktop native code. And in particular, it means supporting features like threads. Modern CPUs are multi-core and also will tend to be multi-threaded. And so we've put a lot of effort into providing a subset of POSIX threads in native client. Also sometimes known as enough rope to hang yourself. But we're also providing abstractions on top of the threads to make them easier to use. For example, Intel's thread building blocks builds cleanly on top of native client, and that's a kind of a higher level interface. Another important performance feature, which I already mentioned briefly, is vector instructions. We'll be showing you an example today of an application that uses SSE instructions to accelerate photo processing. And last but not least, for the people who really need the highest level of performance available in their applications, we make it relatively straightforward to use hand-coded assembler. For the small number of people who are actually interested in doing that, but for the really high-end performance-oriented things, the computational kernels, animation applications, that sort of thing, all that performance is available, and substantially as available as in a desktop programming environment. So, what does this mean for the web? What are the new things that we think native client will enable? Well, as an example, by giving this CPU performance, making it available in web applications, we think we can enable safer multimedia codecs. You'll be able to have a multimedia codec that's embedded in a safe environment instead of running as unconstrained native code. We'll show you some examples, and we have other examples in our open source project, of real-time audio and video synthesis. This is animation, right? So substantially more ambitious than just displaying a video. We're actually creating the video and then showing it to you. Another thing that's really important in a lot of modern user interfaces and games is physics simulations. You actually need to have Newtonian physics with objects colliding into each other and responding in realistic ways. And again, that's in our Quake demo, which is available in our open source release. You can see an example of that. Just briefly going through the list, audio and video analysis and recognition, things like face recognition, we think should be possible in browser-based applications with native code. Multimedia editors, eventually high-throughput cryptography, and more flexible than just using SSL. You'll be able to encode and decode the content as you determine. And application-specific data compression, which has a potential to give you much more dense representations of domain-specific data than just a generic compression algorithm like gzip. Together with this, with O3D, that is the three-dimensional graphics interfaces for the web that Google has recently introduced, we think we'll be able to enable things like high-quality games that start to approach the quality of things that you're accustomed to seeing on consoles, as well as CAD applications and a whole variety of things. So these are the kind of applications that we want to be able to enable with Native Client. Now, so that's enough for background. What I want to do right now is, and what we're going to spend most of the time on today, is going through some examples of actual Native Client applications that we've built and show you some of the nuts and bolts of how things are put together. Before showing you that, I'm going to go through a series of architecture diagrams so you can sort of see how the pieces, what are the pieces and how they work together before we do the examples. So, suppose, for example, you wanted to write a little game, global cooling, we're going to call it in this case, and it's implemented as a web-based application. It happens to use a native client module. So, being a web-based application, there's going to be some HTML someplace. Now, there's two models that we're going to talk about today for using native client modules. One is as a plug-in, and that's what we're going to talk about in this example. The other is using web workers, emerging HTML standard that you probably heard about yesterday. So in this case, if you're using a plug-in, you'll commonly use an object tag, and there'll be a source argument and a number of other arguments, but there'll be a source argument to the object tag that says where is the content that's going to be activated by the plug-in. When Native Client sees the object tag and the MIME type associated with it, when the browser sees that, it activates the Native Client infrastructure, and in particular, a helper module that knows how to handle the native code and enable it for the web-based application. The browser, when it sees the source argument, is going to download the untrusted native code from a website someplace out on the internet. Now, in the case of climate modeling, we probably will need some physical simulation. And so that's what most of the scenario is going to be based on. But suppose, just for a moment, suppose that somebody was trying to trick you and get you to download and run something dangerous. Okay? So before Native Client is going to enable this module, it's going to pass it through a security inspection, static analysis of the actual machine code to make sure that there are no sharp edges, nothing dangerous. And if it sees a module that breaks the rules, that does some of the things that are explicitly not allowed in Native Client, that module will be rejected, and we will refuse to run it. And that's exactly what will happen for random x86 binaries that you might choose. Because there's a set of instructions, a set of constructs in the machine code that we simply don't allow because they lead to safety problems. But if the Native Client module in question has been built properly and follows all of the rules that we've identified for the system, then it will pass through the security scan. And the next step is to load it into a container that's where it will be contained and allowed to run safely. We actually think of this container as kind of like being in jail, because there's still a set of things that we're not going to allow this native code to do. It's still going to be somewhat constrained. But now that it's activated on your desktop and established and running, we can connect it so it can communicate freely with the browser. And at that point, it's going to be able to actually interact with the browser, and the browser, of course, will be able to interact with it, graphics, events, all that sort of thing. And so we've got our native client-enabled web application. So that's a high-level model of what's going on. Just to be explicit about a couple of details, a couple of nuances of the system. We run the native client modules in their own address space, and that's actually mostly for exception isolation. We don't need that isolation for memory protection. We've actually implemented that in our sandbox, but exception handling is more challenging. The operating systems don't know how to handle exceptions except by killing the task. So by putting the native client process module in its own process, we know that we prevent the operating system from terminating the browser. Okay. Another thing is the communication interface that's indicated with the arrows there allows for simple message passing communication. In addition to that, something that we've done that's really very powerful is we provide a shared memory. You can establish shared memory regions between the native client module and the browser. And that's essential for doing things like graphics that require really high communications throughput. The shared memory regions also allow you to implement things like spin locks in the case that you need really high frequency communication. So although you can actually do pretty well in terms of latency with the message passing interface too. So that's the architecture at a really high level. And keep this in mind as we go through the three examples. I want to tell you a little bit about security of native client, because it's a legitimate concern for anybody who's ever used an ActiveX or an NPAPI control. And it's really what we spent most of our time on so far in the project. Our goal, like I mentioned earlier, is to make native code at least as safe as JavaScript and HTML and the other things that people basically take for granted in web content. So some examples of steps that we've taken to make native client safer. Firstly, multiple internal security reviews. We code review all our code. That's a standard Google practice. And anything that gets presented publicly from Google goes through a design review and an implementation review. The implementation review is a really fun one. That's when we hire all these scary black hat guys, and they spend time, they get paid for finding bugs in our code. So we managed to survive that. But that wasn't enough, actually. We felt compelled to do more. So we've open sourced the system. The system has been open sourced since December 8th. And we've encouraged public critical review, in part by submitting papers to prestigious technical conferences. We recently had a publication in IEEE Security and Privacy, which is a really good security conference. And more than that, we held a security contest. We actually challenged the community to find bugs in our system, and we're going to be paying cold, hard cash to the people who have found the most interesting exploits. That contest actually ran for about 2 months, ending on the 5th of May. And just some kind of background on what we put ourselves through. Over 400 teams signed up to compete in this contest, and over 600 individuals. Of those people, there were only 22 issues submitted that were actually valid. Valid in the sense that we agreed they were a vulnerability of any sort. And I provided a little high-level profile of the issues that we saw. Most of them were related to browser integration, issues with dealing with NPAPI or memory allocation and management in that context. There are a couple of issues with the inner sandbox too. That's that validator that does the static analysis of the program. And to just give you that next level of detail, I wanted to share with you a couple of the more interesting issues that we saw in the contest. Now you can see the entire list of issues if you go to the native client code site. But just kind of for the purpose of the talk here, one interesting bug, the native client system relies on being able to disassemble the program accurately and understand all possible control flow. And so this first bug was an example where we had a control flow analysis issue. Now, the native client system has disallowed the x86 prefix byte for 16-bit address computation, adder 16 it's commonly called. And that's important because that lets you do kinds of address calculations that let you jump anywhere in the code, so defeating our intention of being able to reliably disassemble the program. Well, but we missed a case of that. It turns out that you can use a different prefix, the data 16 prefix, to do 16-bit address calculations for a certain set of jump instructions that we neglected. And so it happened to be 2-byte jump instructions. So the solution to address this problem and prevent this arbitrary control flow transfer is to disallow the data 16 instruction for a bunch of additional 2-byte instructions that we hadn't considered before. And furthermore, we took an additional step of unmapping the entire first 64 kilobits of the address space of the native client module, so that any 16-bit address would never be a valid address for a control flow transfer. So one other quick example. I know this is a little bit gritty, but just want to make the point of the kinds of steps we're taking to secure the system. There was a stack smashing attack vulnerability found dealing with the E-flag's direction flag. Now, on the x86 architecture, you probably know there's some repeat instructions that can be used to copy very long strings. And with those move instructions, there's a flag that determines whether it copies forwards or backwards. Well, it turns out there was a place where we didn't check those flags before invoking system calls of the native operating system. And furthermore, there was a Windows system call that used a repeat MoveS instruction without checking the direction flag first. So the combination of those two problems meant that you could actually use the Windows stack smashing prevention code to do a stack smashing attack, which is kind of ironic. Fortunately, again, the solution was not too difficult. It was just a matter of clearing the flags carefully before every time we invoke anybody's system calls. And so that gives you hopefully a little bit of intuition about the kind of tricky stuff that is involved if you're going to attempt to defeat this system. The good news, and the thing that we're actually very pleased about, is although there were a few, 22 issues submitted to the contest, there were no real fundamental architectural issues. They were all basically implementation defects, and the kind of defects that we had no trouble fixing in a matter of days. So that kind of reinforced our belief that it's possible to implement a system that achieves a substantial level of safety. Okay. So before we dive into the details of the examples, I wanted to tell you a little bit about where the project is today and where we're going in the future. Today, native client is delivered as a NPAPI plugin. This design is really mostly intended for a research release, and it means that anybody who has any NPAPI-capable browser, including Opera, Safari, Firefox, Chrome, any of those, can use our plugin and explore creating and even trying to find security defects in the system. The system, as you might have noticed from my discussion, does rely quite heavily on x86 machine code. That's sort of a fundamental part of how we make things secure. And the graphics support we provide today is pretty much limited to raster graphics, which means software graphics, not hardware accelerated bit operations. Our code development tree, for those of you who have sent us change lists, is hosted internally. It turns out that these are basically details for the research release, and going forward, we're thinking much more about a developer-oriented system. So some of the implications of that is rather than designing the system as an NPAPI plugin, we want it to be built directly into the browser. The Web Workers demo that we're going to be showing is a first example of that. But we're also going to be preparing revisions to the current version of NPAPI, things that enhance the portability and performance of NPAPI as it's currently designed, so that this will be a better interface for hosting safer plugins in web browsers. We're also, we believe very strongly that the web should be portable, and it is not really appropriate to lock all future web content that uses this kind of acceleration into a single instruction set. So we're putting a lot of effort currently into 64-bit x86 support and also ARM support. Now, in terms of delivering better graphics, we've got a collaboration with the O3D team to deliver 3D graphics and make it available to native code. A lot of developers have asked about an OpenGL interface and the possibility of providing an OpenGL interface in native client. And that's definitely a request that we'd like to be able to respond to at some point. And then finally, the other detail I wanted to mention is we're moving into a public SVN repository right alongside the Chrome repository, which will make it much easier for external developers to make contributions directly into the system. So, the demos that we're going to show you today actually preview some functionality that is not in our research release yet, but is a part of what we're working on to provide in our developer release. And the first example is native web workers. Now, you've heard some discussion in other sessions here at Google I/O about web workers, a way of creating threads in JavaScript. Well, native web workers are just like web workers, except instead of being written in JavaScript, they're written in native code. But otherwise, they have the same execution model and the same interfaces as web workers. In particular, web workers supports no shared data. There's no way to share data between web workers and the browser. And as a consequence of that, web workers can't actually do direct DOM access. Web workers support a post message API as well as XML HTTP requests to make HTTP requests of the hosting website, and open database to provide access to stable storage. And you can see lots of details about the web worker specification at the URL that we provided up there. Our goals in native client for native web workers are firstly to support web workers in other languages besides JavaScript, for example, C, C++, or Ruby. Also, we still want to maintain the simplicity of the web worker model, which was very deliberately designed to prevent the kinds of race conditions and other kinds of issues that can make threaded programming sometimes very difficult. And provide an interface that's basically appropriate for low-frequency applications, things where like you make a request and then, a second or so later, you get the information back and can use it. So, as an example of that, David Sear, tech lead for the Native Client project, is going to walk you through what we've done with web workers for Native Client.
Okay, thanks, Brad. As Brad said, I'm going to be talking a little bit about some early work that we're doing on supporting native web workers. As you probably heard Matt Papakipos talk yesterday about web workers and about the sort of programming paradigm that it supports. I'm going to show you how we think one possible direction of embedding Native Client into this sort of programming model would be used. So here's a kind of a classic example of an application that you might like to thread. It's a compute-intensive application. In this case, I'm going to be showing you computing a Mandelbrot picture, and each one of those boxes is eventually going to be populated with some colored bits. Mandelbrot is a compute-intensive application. Basically, you're computing a bunch of floating point values for each one of the points in the region. And we've taken this as a little demo and parallelized it by splitting each one of those squares into 4 tiles. Each tile will be handled by a separate web worker. See, on these modern multi-core processors, you could have 4 web workers, each having access to 1 core. And you'll be able to update Adobe, it appears, at the moment. Anyway, So here's the JavaScript code that does a typical web worker sort of application, the one that I was talking about before. There's a doubly nested loop. That's actually just walking over each of the tiles. That's here. And each one of the tiles is computed by an instance of a web worker, and that's created by this just new worker. And in the HTML5 spec, the worker URL is a JavaScript script, and then communication is back from the web worker by assigning this onMessage property to be a function that takes an event, and that event will, in this case, be the result of the computation. Basically, it's a big string containing the pixel RGB values, And then there's some GUI here for putting the RGB up on the screen. The host JavaScript, the JavaScript actually that runs in the browser, is able to talk to the worker by using these post message APIs. And so in this case, each one of the tiles is started off. There's an on message bound for it that will enqueue the tile and eventually put it up on the screen when the last tile is received. And then the tile computation is actually started by being passed a string that says, which tile are you and how big is the tile? So the code then in the worker JavaScript has a sort of similar flavor. There's an on message that says, when I get a message from the host JavaScript, what am I going to do? In this case, I'm going to do an awful lot of floating point stuff and then some computing RGB values from the floating point. And eventually, I'm going to put together a big string that contains all the RGB pixel values, and I'm going to do a post message to pass that string back to the host JavaScript in the browser. So pretty straightforward, I think. So our approach to this for native web workers will actually use the same API. The initial work we're doing just basically detects using a different URL, in our case looking for .nexe, or native executable. That's our name for native client executables. If you see new worker with the worker URL being mandel.nexe instead of mandel.js, well, then you will start a native client execution environment and run the code that was contained in that executable. Now, you'll be seeing this again in Nicholas's demo in just a second. We have defined a native client. There's an RPC interface, which we call the simple RPC or SRPC interface. And SRPC methods are always of this sort of prototype where you basically have a list of input arguments and a list of return values. And so what we have done for this is we bind one native client RPC method to be post message. And so that means if an RPC to post message from the host JavaScript is called, it will invoke this function called mandel worker up here. And mandel worker will extract its parameters. In this case, we're passing strings as methods. The web worker interface allows you to pass slightly richer data types, but I'm not talking about that in this particular example. So you can extract the string value by saying the first input argument, and it's a string. So you extract that. Then it does some computing. This mandel computes each one of the point values and produces a string. And then when it's done producing the string, it will call a post message API, which is a post message back to the browser saying, here's the result of my string. So other than the fact that this is C, it looks an awful lot like the JavaScript sort of approach. We've defined an RPC handler that does some computes and eventually does a post message back to the host JavaScript. So the two are very similar. So, and forgive me, the posting things to the screen is actually slower than doing most of the computes in these things. So the performance delta is not obvious, but if the timing is actually done, you'll see that the native one is quite a bit faster than the JavaScript. But you can see the two things have functionally the same behavior. The same host JavaScript code is used for both the JavaScript web worker and the native client web worker. And we'll be developing some more applications to try and showcase the power of native executables in this setting as the web worker support becomes more and more mature. It should be said that Brad said we're going live soon with our SVN tree. The demo code is in the repository that will be going out. The web worker support will be appearing in a Chrome release that hasn't yet gone out. So sometime over the next couple of weeks, we hope to get that out. So you'll be able to try this. And with that, I'll turn it back to Brad.
Thanks, David. Okay. So, native web workers is probably going to be the simplest interface, simplest way to use native code and get native code performance in your web applications. For people who want more interactivity, who want to write the kind of high-frequency applications like animation or audio or video decoding, we're planning revisions to NPAPI. We currently have NPAPI support in our current system, but to address some of the portability and performance issues that we've found in that API. Now, for those of you who are familiar with browser plugins, you probably recognize that use today is quite limited. There's a lot of well-known security issues, most of which hopefully we've convinced that we can do something about. We've convinced you we can do something about. Pop-up boxes asking people questions that they really shouldn't be asked in the first place. Overall web portability and the ubiquity of content just kind of falls apart. We're determined to create a better future for native plugins by addressing some of the well-known misfeatures of NPAPI and ActiveX. And compared to web workers, we're going to actually address some of the limitations of that system. We will support shared data. We will provide the kinds of things you need to implement high-frequency applications. And we'll also be providing mechanisms through NPAPI to provide synchronous DOM access. So, as a first example of how these more direct interfaces work, I want to show you a video player, a video decoder that we've been working on. Now, another thing I want to point out, and the main point of this example, is just how simple it is to take an existing Linux application and make it work under native client. This particular video decoder is something that had been bouncing around inside Google for a while. The original test program took an H.264 encoded video, and wrote it as raw frames into a file on disk. It only took 20 lines of source code changes to take that original test program and turn it into a program that's a simple native client video player. About 210 additional lines were required to add audio and frame rate control. But for now, I just want to focus on the video modifications. I'm actually going to walk you through the 20 lines of source changes that it took to make this thing run in native client. Firstly, in order to use the multimedia subsystem that native client provides, and this subsystem, by the way, leverages the communications substrate, NPAPI, and the shared memory system that I mentioned earlier, you make this call to NACL multimedia init, then 4 lines of error checking. And then after initializing the multimedia system, the next highlighted line to NACL video init initializes the video subsystem of the multimedia system. 4 more lines of error checking. We're going to null out a pointer so that the application doesn't try and write all of this video to a file on disk. And that's the initialization code. The next change we had to make is when the frame becomes available to actually display it on the screen. So the original internal representation of frames in this system was in YV12. We used this call, which was already a part of the decoder, to create an RGB representation. And then NACL video update takes the RGB frame and causes it to be blitted onto the screen, the screen real estate that was established with the earlier initialization calls. And that's it, actually. Those lines are all you need to actually get the video displaying on the screen. Now, there's a couple of includes that had to be fixed, and there was a shutdown that I didn't bother including, but that's pretty much all it took. So the next thing I wanted to actually show you is a demonstration of the decoder. I was actually going to build it for you first, just so you can see that, that building a native client module is actually not that different from building anything else. Surprise, surprise. The path to the compiler is a little bit messy, but after that, this is pretty much just a normal old invocation of GCC. It's got a bunch of source files from the decoder itself, and then starting around here, we're pulling in some additional source files that implement the audio part of the system. And now it's built. So the next thing I want to do is actually invoke it. Now I'm going to, for the purposes of the demo, invoke it the way typing the whole command line out. We need to, and I'm not going to be running this in the browser. You'll notice I'm going to use the debug environment that we use ourselves and that we provide as a part of our open source release. So let's see, staging. There's a program called Cell Loader, which is a container for running these native client modules outside of the browser. I'm going to pass it the debug flag, and that's because since we're not running in a browser, I need to get the video file off the file system. And so the debug flag is going to actually take down the firewall that prevents file system access and let us access the file system directly. If you run without the debug flag, then you wouldn't be able to open any files or see any of the local file system. Then I'll next specify the native client module, which is called G264 release.nexe. That's what we built up here someplace. And lastly, the name of the video. And so we get to enjoy a 47-second ad for Google Chrome. Turn the volume up here. Right. So a couple of things I wanted to point out while we're watching the squirrel run around. This is just like The Office, by the way. This is a portable binary. It will run on Windows, Mac, and Linux. And the native client modules will run in NPAPI browsers, Opera, Safari, Firefox, and Chrome. It's entirely portable. We're getting pretty close to the same performance as the original decoder. In addition, in native client, we've gone through a lot of effort to maintain the kind of facilities you need to actually do real-time applications in a reasonable way, including access to the timestamp counter and performance for other system calls that allow you to manage time effectively. So that's our video decoder, and hopefully you all saw it ran pretty much like a normal old video decoder. That's the whole point, right? The next demo we want to show you is actually an example of the same kind of interface being used, but running in a web application. So we're going to have most of the user interface implemented in JavaScript, and the fast part, the image manipulation, is going to be implemented in native code. And I'd like to introduce Nicholas Fullagar now. He wrote this application, and he's another one of the lead developers on the native client team.
Thanks, Brad. Hello. So today I'm going to demonstrate native client darkroom. And let's see. And first we'll do a little walkthrough in Chrome and launch the application. And note, it's just like visiting any other web page. If you have the native client plugin installed, there's nothing else you need. So we're going to open the photo, and it's a nice little picture. And so why native client? Why would you need native client for this? Let's say, for example, this photo is something that you've uploaded somewhere, and you want your friends to be able to critique it for you. And they want to make suggestions about, well, maybe it looks better if it's in black and white, or maybe it will look better if you add a little bit more contrast to the image. These are all non-destructive edits, so we still have the original image available to us. This is nice because if you have it sitting on the server, you don't want to start creating multiple copies for every edit. You really just want to send around the values of the sliders that people have suggested. So these sliders are implemented in JavaScript and HTML, and they control most of the GUI for this application. This area here is in native client, and it's running the native C code. And you can see it updates pretty quickly. We can zoom in, we can zoom out. We've got bitmap scaling done in native client. We've got some geometry operations. You can rotate the image. And these are all occurring fairly quickly. And this is modeled after some of the popular photo editing software that you may have experience with. So the other important thing to keep in mind is that this same web page will work on Linux, Mac, and Windows as long as they have the native client plugin installed. So next we'll look at the source code for a little bit. Here's the photo HTML code. And what we're going to look for here is what happens when you update the angle. So here we have a little bit of HTML that sets up the slider that the user can adjust to change the angle. And we've added an update function, a JavaScript function that gets called every time the slider gets changed. That calls this JavaScript function, which passes in the value of the slider. And what we've done is we have a native client object which has simple RPC calls bound to it. And one of these calls is update angle, and we pass along the value of the slider. This now jumps into C code. And as David showed earlier, we have these SRPC methods that we've set up. And we've got the name of the JavaScript function, of the JavaScript binding, and it passes one argument, which is an integer. And it calls this C function in our C code. So jumping to that C function, we've got the parameters coming in, and we know the first parameter is going to be an integer, so we extract it here, and we convert that slider value to a float, and then we pass it to the darkroom class and call it setAngle function. Now it should be noted, this SRPC is happening asynchronously on a listening thread, so we're going to very quickly just pass it over to the darkroom class, and in its own application thread, when we're rendering the photo, we'll take into account the new angle. Now we're going to make a bit of a jump, and we're going to go straight into the low-level code that does the pixel processing when that image rotation occurs. This is again in C code, and we do the rotation as a product of 3 shears. We do 2 horizontal shears and a vertical shear, and that makes some of the filtering a little bit easier because we just filter in 1 dimension instead of having to filter in 2 dimensions. So this is, if you've written low-level pixel blitting code, this should look pretty straightforward. There's quite a bit of setup code here for calculating what the filter value should be, and if we go further down, we get to the actual pixel processing loop that takes the image and does the shear. So for each pixel, we're going to read the source, and if we go outside of range, we're going to read the border color, and then we're going to apply some SSE intrinsic code, vector instructions, to apply the filter that's necessary to shear the pixels. Then we combine the result and store it in the destination. So this is what's driving the low-level image rotation that we looked at earlier. When I make this slider move and we see the image rotate. So this example will be online soon. Keep your eye on Google Code, and thanks for listening. Thanks.
Okay, so with that, we're pretty much at the end here. Our project, like I mentioned, has been open source since December, and we would really be delighted if people had ideas for how to move the system forward or had an application that they thought would benefit from the speed of native code in the browser. I wanted to mention at 1 o'clock, which is in about 15 minutes, there's a fireside chat where some of the product management staff will be taking questions about native client and other client technologies. And we'll be holding office hours, the native client team, at 3 o'clock. And we'd be happy to tell you more about these examples, other examples in our open source release, or if you've got a piece of code or an idea for a system that you think might benefit from this, we'd be there to talk with you about it. So right now, we've got plenty of time for questions, and we'd be happy to hear about questions or ideas about native client. Can you guys join me up here, please?
The mic, or?
Please, yeah, it's being filmed.
You mentioned explicitly encryption, and you said eventually. Could you elaborate?
Well, I guess only a little bit, since we don't have any specific plans. But there's a high-level notion of, today SSL takes an entire web page and encrypts all of it. And there's situations where it might be beneficial to actually only encrypt part of it. But doing that over SSL is messy. If, on the other hand, you had encryption tunneled through an HTTP request, it would give some more flexibility.
My specific problem is encryption and signing using X509 certificates under JavaScript control. And right now, I am forced into using IE for the ActiveX controls. And I would love an alternative if that's on the horizon.
Very interesting. Well, the one thing that I can promise you about native client is if it's pure computation, then we can deliver it as almost as fast as what you get with the native CPU. So this sounds like actually a pretty good application.
Okay, thanks.
Other questions? Other questions about native client?
Hi. What's the lifespan of the web worker itself? Like, how many pages does it remain? If I move forward, how long will the web worker, the native version of it, remain?
That's a good question, and David might know the details of this better than me. The lifetime of a web worker.
The lifetime of the web worker is actually this. Once the object has been created, as long as there's a reference to it, I mean, it's basically a reference-counted object in the JavaScript execution environment, just like anything else. So as long as there's a handle still held to the worker, that process is still alive. There's some startup and shutdown capabilities as well. So I mean, I can send an explicit message to shut down the web worker, but
so if I navigate to a page forward and if I come back, have I lost it?
We're not currently working on persistent web workers that Matt talked about. So in that case, you'd be sort of you'd restart the web worker. Yes.
Yeah, but there is this proposal for a thing called persistent web workers, which would give a worker thread a lifetime that's independent of the lifetime of any particular page. And as that kind of progresses in terms of the JavaScript version and in terms of standardization, you should expect the native web workers to follow.
Okay, thanks.
Any other questions? No? Okay, well, enjoy the rest of the Google I.O., and thanks very much for listening to our talk about native client.